Hello friends, welcome you all to the 22nd lecture on function analysis and its application. In this lecture, we will discuss the dual space of LPn, L1n and L infinity n. This is the content of today's lecture, dual space of LPn, L1n and L infinity n. Representation theorems for functionals. If L is Banach space, we find the another Banach space L dash, which is isometrically isomorphic to L star. If L star and the corresponding element of L dash is Y, then for each x belonging to L, the value of fx is given by an infinite series involving x and y or some kind of integrals. Before finding the conjugate spaces for infinite dimensional Banach space, we shall find them for some finite dimensional Banach space. Okay, like before discussing conjugate space of LP, L1 and L infinity, so before of these, we shall discuss the conjugate of finite dimensional Banach space. Theorem: if L is linear space of n tuples, then dual space of LPn is LQn and dual space of L1n equal to L infinity n and dual space of L infinity n equal to L1n, okay, where 1 upon P plus 1 upon Q is equal to 1. So roughly we can see the dual space of LP is LQ. Okay, if we put P is equal to 1, okay, then 1 upon Q is equal to 0, that is Q is infinity. Okay, so dual space of L1n is L infinity n. And if we put P is equal to infinity, then we get Q is equal to 1. Okay, if P is equal to 1, that is 1 upon P 0, then we have 1 upon Q is equal to 1, then Q is equal to 1. So here L infinity n, dual space of L infinity n is L1n. Let us prove it. Let E1, E2 and so on En be the standard basis for L, so that for any x belonging to L, that is x is n tuples of x1, x2 and so on xn, can be expressed as x equal to x1 E1 plus x2 E2 plus and so on xn En equal to summation of I is equal to 1 to n xi ei. Okay, where E1 equal to 1, 0, 0, 0 up to n times. E2 0, 1, 0 and so on 0 n times. Okay, that is Ei equal to 0, 0 at ith place 1, 0, 0, 0 n times. Okay, so here we can see easily x is equal to n tuples of x1, x2 and so on xn can be expressed as x1 E1 plus x2 into E2 plus and so on xn into En. And in short way, we can write this summation I is equal to 1 to n xi ei. If f is scalar valued linear functional defined on L, that is f such that L to k scalar valued function, that is f belonging to L star. L star is beta of Lk, set of all bounded linear functional. Then we get fx. Here x is equal to x1 e1 plus x2 e2 plus and so on xn en. So taking functional on both sides, that is fx is equal to x1 f of e1 plus x2 f of e2 plus and so on xn f of en. Here x1, x2 and so on xn are constant and e1, e2 and so on en are vector. Okay. So fx equal to x1 into f of e1 plus x2 into f of e2 plus and so on xn f of en. That is summation I is equal to 1 to n xi f of ei. Okay. Equation 1 shows that f determines and determined by n scalar yi equal to f of ei. Okay. That is y1 is equal to f of e1, y2 is equal to f of e2 and so on yn is equal to f of en. Then the mapping y this to f, that is tf, collection of f of ei, that is tf is equal to n tuples of f of e1, f of e2 and so on f of en, which is the element of L dash. Okay, where f of x is equal to summation I is equal to 1 to n xi yi. This one f of x is equal to this can be written as yi, where fx this is an isomorphism of L onto the linear space L dash of all functions f. With the help of these preliminaries, we shall establish first, second and third respectively. This one. Okay. Now we prove first. In this case, consider L is equal to LPN. P lies between 1 to infinity. And we know that f defined above is continuous and L dash represents the set of all continuous linear functional on LPN. So that L dash equal to LPN star. Now we determine the norm for the y, which makes f an isometric isomorphism. Therefore, T such that LPN star to LQN, where LPN star equal to L dash. Okay. So, for 1 less than P less than infinity, we show that LPN star is equal to LQN. Let X is the element of LPN. Then we have norm xp equal to summation I is equal to 1 to n mod xi power p whole power 1 by p. Okay. We know that the norm for LPN, if x belonging to LPN, so norm x is equal to this one. Now from equation 1 and using Holder's inequality, we get here equation 1 f of x is equal to summation I is equal to 1 to n xi yi. So f of x equal to summation I is equal to 1 to n xi yi, taking the modulus of both sides. So mod fx is equal to mod of this summation I is equal to 1 to n xi yi. This is less or equal to summation I is equal to 1 to n mod xi yi. Applying Holder's inequality, this less or equal to summation I is equal to 1 to n mod xi power p whole power 1 by p into summation I is equal to 1 to n mod yi power q whole power 1 by q. So we have mod fx less or equal to norm x summation I is equal to 1 to n mod y I power q whole power 1 by q. Why? Because here norm x is equal to this. So we can write this one as norm xp. And also we know that norm f equal to supremum of mod fx upon norm x, where norm x not equal to 0. So this inequality can be written as this. Okay, why? Because dividing both sides of norm xp, so mod fx upon norm x, this is supremum value of mod fx upon norm x, that is norm f. So divided by norm x both sides, so left side norm f and right side this one. Hence norm f less or equal to summation I is equal to 1 to n mod y I power q whole power 1 by q. Okay, yi is f of ei. So norm f less or equal to summation I is equal to 1 to n mod f of ei power q whole power 1 by q. This is the collection of tf. Here collection of f of ei is tf. Okay. So this can be written as norm of tf lqn. Why? Because we know that if x is equal to x1, x2 and so on xn, then norm of x is equal to summation mod xi power, if here qth norm, so this is power q whole power 1 by q. Okay, so as per this, here tf is equal to n tuples of f ei. So this can be written as norm of tf. Okay, and here f is the element of LPN star. Okay, so here f is the element of L star. So here f is the element of LPN star, that is this one is norm for LPN star. Okay, so norm f LPN star less or equal to norm TF LQN. Equation 2. Now we consider the vector x defined by xi is equal to mod yi power q upon yi, when yi not equal to 0 and 0 when yi is equal to 0. Okay, we consider this vector. Then norm xp equal to, here xi is equal to mod yi power q upon yi. It means x1, here for this x equal to y1 power q upon y1 mod y2 power q upon y2 and so on mod yn power q upon yn. So n tuples of this. So norm of x can be defined summation I is equal to 1 to n mod yi power q upon yi power p whole power 1 by p. Okay. Also we know that 1 upon p plus 1 upon q is equal to 1. So taking LCM PQ, that is q plus p equal to p into q, that is this one. So taking p this side, okay, then q is equal to p into q minus 1. Using this, norm xp is equal to summation I is equal to 1 to n, here mod yi power q and this is also mod y because this mod. So this is mod yi power q minus 1 into p. Okay, and q minus 1 into p is q. So this can be written as summation I is equal to 1 to n mod yi power q whole power 1 by p. Now fx is equal to summation I is equal to 1 to n xi yi. Okay, fx can be expressed as this. Here xi is this one. So putting the value of xi here, we get summation I is equal to 1 to n mod yi power q upon yi into yi. So it cancelled out. We have summation I is equal to 1 to n mod yi power q. So this implies that summation I is equal to 1 to n mod yi power q equal to mod fx. Okay, and fx is linear functional, then less or equal to norm f norm x. Okay, and the value of norm x is summation I is equal to 1 to n mod yi power q whole power 1 by p. Clear? So we can put the value of norm x here. So we get summation I is equal to 1 to n mod yi power q less or equal to norm f, and summation I is equal to 1 to n mod yi power q whole power 1 by p. So dividing by this both sides, summation I is equal to 1 to n mod yi power q whole power 1 by p. So left side is summation I is equal to 1 to n mod yi power q whole power 1 minus 1 by p less or equal to norm f. Okay, again this one mod yi power q, so 1 upon p plus 1 upon q is equal to 1. Okay, so 1 minus 1 upon p is 1 upon q. So this implies that summation I is equal to 1 to n mod yi power q whole power 1 by q less or equal to norm f. This implies that summation I is equal to 1 to n mod f of ei power q whole power 1 by q, because yi is f of ei. So this can be written as under q norm, that is LQN, norm TF less or equal to norm F. Okay, from equation 2 and 7. Here in 7, norm TF LQN less or equal to norm F, and in 2 just reverse, F LPN star less or equal to norm TF LQN. Okay, so from equation 2 and equation 7, we have norm TF equal to norm F. Okay, so LQN is LPN star here. So this is isometric isomorphism. Hence LPN star is LQN. Hence first is proved here. Second, if L is L1n and let x belonging to L1n, we have norm x is equal to summation I is equal to 1 to n mod xi. Here we know that norm p, defined norm x is equal to summation mod xi power p whole power 1 by p. So p is 1 here. In above condition, the first here p is 1 in this case. Okay, that is L is L1n. Let x belonging to L1n, then norm x is summation mod xi. Let L star represent the set of all continuous linear functional on L1n. That is L star is star of L1n. That is conjugate space of L1n. Now we determine the norm of y, which makes y to f an isometric isomorphism to L infinity n. Therefore, T such that L1 n star to L infinity n, where L1 n star equal to L dash. Now from equation 1, mod fx equal to mod of summation I is equal to 1 to n xi yi. This is less or equal to I is equal to 1 to n mod xi mod yi. So value of this one is mod x1 mod y1 plus mod x2 mod y2 plus and so on mod xn mod yn. Okay, we can take the max yi, which one larger? Suppose yi term is maximum. So max yi common. So this can be written as summation I is equal to 1 to n mod xi. Okay. So mod fx less or equal to max mod yi summation I is equal to 1 to n mod xi. So this term, this is as normax. Okay. So mod fx less or equal to max mod yi into normax. Also we know that supremum of mod fx upon norm x is norm f. So equation 9 can be written as norm f less or equal to max of mod yi. This one. Okay. And yi is f of ei. That is norm f less or equal to max f of ei. So max of mod f of ei, that is norm of tf under L infinity n norm. Okay. Therefore, norm f L1 n star less or equal to norm tf L infinity n. Now consider the vector x defined as follows. If mod yi equal to max of mod yi, then define the vector x. So ith point of vector x defined as xi is equal to mod yi upon yi, when mod yi is max value of mod yi and 0 otherwise. Therefore, norm x equal to summation I is equal to 1 to n mod xi. Okay. Norm x belonging to L, here L is L1 in n. So norm x is equal to summation I is equal to 1 to n mod xi, that is mod x1 plus mod x2 plus and so on mod xn. From equation 11, this xk is equal to 0, k not equal to I. Then from equation 12, norm x is equal to each term 0 except mod xi. Mod xi is mod yi upon yi, because here xi equal to mod y upon yi. So this one, that is norm x is equal to 1. Further from equation 1 and 11, we have mod fx is equal to mod summation xi yi equal to mod summation mod yi upon yi. Okay, because here we put the value of xi from equation 11. Y cancel, that is we have summation I is equal to 1 to n mod yi, that is mod yi, because here mod yi is max of yi. Okay, and other is 0. Hence max of mod yi equal to mod of fx. F is linear functional, then it is less or equal to norm f into norm x. And norm x is equal to 1. Then max of mod yi less or equal to norm f. Yi is f of ei. That is max of f of ei less or equal to norm f. That is max of mod yi can be written as norm of Tf under L infinity norm. So this implies that Tf under L infinity n norm less or equal to F under L1 n star. From equation 10 and 15 we have norm Tf under L infinity n norm equal to norm of f, which is L1 n star. That is y to f is an isometric isomorphism of L1 n to L infinity n. Hence L1 n star is L infinity n. That is dual of L1 n is L infinity n. Third, let L equal to L infinity n and let x belonging to L infinity n. We have norm x defined max of mod xi as per the definition of L infinity n norm. Let L star represent the set of all continuous linear functionals on L infinity n so that L star equal to star of L infinity n. We shall determine the norm y which makes y to f an isometric isomorphism to L1n. Therefore, T such that L infinity n star to L1n, where L infinity n star equal to L dash. Now from equation 1, f of x equal to summation I is equal to 1 to n xi yi. So taking modulus of both sides of the equation 1, we have mod fx is equal to mod of summation I is equal to 1 to n xi yi. This less or equal to summation I is equal to 1 to n mod xi mod yi. Again, this is the summation I is equal to 1 to n. So this can be written as mod x1 mod y1 plus mod x2 mod y2 plus mod x3 mod y3 and so on mod xn mod yn. So taking x1 as max of xi, x2 also max of xi and so on, each mod xi, that is max of mod xi. So max of mod xi can be common. Okay, this is also less or equal to max of mod xi summation I is equal to 1 to n mod yi. And max of mod xi is norm x. So we can write mod fx less or equal to summation I is equal to 1 to n mod yi into norm x. Also we know that norm f is equal to supremum of mod fx upon norm x. So this divided by norm x of both sides. So we get norm f less or equal to summation I is equal to 1 to n mod yi. Yi is f of ei. So norm f less or equal to summation f of ei. That is f of ei is L1 norm. Okay. So norm f L infinity n star less or equal to norm of Tf L1n norm. Now we consider the vector x defined by this. Xi is equal to mod yi upon yi. When yi not equal to 0 and 0 when yi is equal to 0. Okay. So x has n tuples. So ith point of x is mod yi upon yi when yi not equal to 0 and 0 when yi is equal to 0. Hence from equation 19, norm x equal to max of mod xi because x belonging to L infinity n. Okay, so norm x is equal to max of mod xi and xi is this. So max of mod yi upon yi, that is mod yi upon mod yi, that is 1. So norm x is equal to 1. And from 1 and 19, one is fx is equal to summation I is equal to 1 to n xi yi, that is mod fx is equal to mod of summation I is equal to 1 to n, putting the value of xi from equation 19. Mod yi upon yi into yi. So yi cancel out. So we have summation I is equal to 1 to n mod yi. So from 20 and 21, here norm x is equal to 1. So and 21 is mod fx. So from equation 21 we have mod summation I is equal to 1 to n mod yi equal to mod fx. F is linear functional. So it can be written as less or equal to norm f norm x. And from 20, norm x is equal to 1. Okay. So summation I is equal to 1 to n mod yi less or equal to norm f. Yi is f of ei. Summation I is equal to 1 to n mod f of ei less or equal to norm f. F of ei is the element of L dash. Okay. So norm TF under L1n norm less or equal to norm F L infinity n star. Okay. So from 18 and 22, here 18 and 22, we get norm TF L1n equal to norm F L1n star. So this y to f is an isometric isomorphism. Hence L infinity n star is L1 n, that is dual of L infinity n is L1 n. In this lecture we have discussed the dual space of LPn, L1n and L infinity n. These are the references which have been used in this lecture. Function analysis, Dover publications by George Beckman and Lawrence Naresy. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterwooding. Thank you.